Hi. First off, just wanted to extend thank yous to PTV for allowing WSP and Amin and I to share some findings that we had for a previous project. It's not every day where technical staff are able to do what we love and also get to share it with a wide audience. So really appreciate this opportunity to share and to grow the knowledge in the industry and for all Vissim users. So very excited about presenting today. So today we'll be, excuse me, going over a transit facility. This was a project that was conducted with the New York and the Seattle team at WSP. For non-disclosure reasons, we're unable to share what facility it is, but you might guess knowing that it's a very congested and urban area in the country, and the transit facility is prospected to have more than 1,000 vehicles per hour in this facility, or that's the aim for growth. So lots of exciting things in a very urban and congested area. So we'll speak to some modeling techniques that we deployed that are fairly new to Vissim. So first we'll go over the project introductions. We'll discuss some of the Vissim parameters that we had considered. Oftentimes people say Vissim modeling is more of an art than a technique or an engineering sometimes, because there's multiple ways, multiple paths to the same destination. So we'll be discussing some of the parameters that we decided to use. And then Amin, our Seattle counterpart, he will go over the actual execution of what we had explored with the user-defined attributes and attribute modifications. And then we'll display the final model and discuss some of the conclusions that we drew, and also speak to some future opportunities that are available for additional exploration. So just to go over some staff, Luke's then unsure if he was able to make it, but he was our staunch supporter. He's the technical advisor to the work. He does a lot of the liaising between the agency, the client that we worked for, and here Amin and I, we executed the Vissim modeling. So this is the key staff that worked on this project. So project introduction, the project premise. So what you're seeing here in this graphic is a adjusted layout of the transit facility. And what you're seeing here is about 30 gates. It's an internal infrastructure, so it's in a building. This is one of the floors, one of many floors. And what you're seeing on the bottom right corner is a storage and staging area where overflow buses or buses that have a more long-term headway are stored and kept. And then the gates are where, you know, passengers are dropped off and picked up. Internal to the four sides here are escalators and sets of elevators that allow for pedestrians to circulate. So this is an internal infrastructure. And this facility operates throughout the day, but the primary peak hours that we had investigated were the AM and PM peak. But the PM peak really exercised the needs, the use of user-defined attributes and attribute modifications that we wanted to go over during the presentation today. So the AM peak was omitted from the presentation, but we had analyzed multiple peak hours. The PM peak, the peak direction, was the departures direction, meaning vehicles would come and pick up passengers and take off. So in the morning, the peak direction would be inbound, and then in the PM peak, the peak direction would be outbound. Of the 30 gates, we had some designated arrivals gates, if you will. We had 2 arrivals parking stalls where vehicles, the fleet would drop off passengers, and then the rest would operate as departures gates where vehicles are coming in and picking up passengers and departing to their respective routes. The agency informed us that their target turn per gate was 6 to 7, and turns per gate meaning each gate would serve between 6 to 7 fleet or vehicles per hour. So that means that you would have at about every 10 minutes, between 8 and 10 minutes, you would have a bus leaving from that respective gate. So of 30, you could imagine 30 gates multiplied by maybe 6 to 7, your ballpark would be around 180 to maybe a little more from this floor. Some project objectives. What you're seeing here in this graphic, I just dropped in some plan view images of elevator banks and bathrooms and escalators just to kind of visually depict what it looks like. But essentially, we have the internal floor plate, and then on the exterior of the building, you have some gates. And so the opportunities that we really wanted to investigate are some ITS strategies to manage demand for transit. So the first that we explored in this project was vehicle queue management. So we'll get into the finer details. Amin will do that, but what you're seeing here are race tracks of the storage area, and then we have some sawtooth spaces as well. So the queue management would allow for vehicles. Of course, you know, the fleet operators could recognize that there's an empty space in front of them if they were physically in the bus, but the queue management system would be able to identify if there's a vacancy in front of that vehicle, because if we have a vehicle stacked in the middle of the queue, then it would reduce the capacity significantly. So there's some opportunities for ITS for queue management. The second is dynamic gate assignment. So because of the limited amount of space on the floor plate, there may be opportunities where buses are stacked where and maybe in the middle of the queue, there's a bus that needs to get to a gate, but there's multiple buses in front of it. Perhaps because of assignment changes, maybe there's a bus breakdown, so there's maybe 1 or 2 buses omitted. There's a lot of, because excuse me, because the context of this location is based in a very congested area, we recognize that there's a lot of bus bunching, vehicles that were unable to make the exact headways. Oftentimes in the PM peak, we had buses that were on demand, leaving from the gates, not at the designated headways, and these were observations that were made for many, many years. So that was something where we wanted to incorporate a dynamic piece to the gate assignment, so that when a gate is vacant, we would want to release vehicles from the staging area and allow for some ITS for some dynamic reaction to what's happening at the gates. The third item is driver and fleet coordination. So again, if there's a vehicle that needs to get to a certain gate and the frontmost or the track leader, whatever vehicle that's in the very front of the tracks, if they were unable, if they're not assigned to anything, then a driver from a vehicle or a fleet, behind the track leader would potentially move to the track leader and get released from the front of the track from the storage and staging area. Bus priority sensors. So on this floor plate, we had two signals, and we're aware that most of the country, there's a lot of TSP that's being deployed across many towns and villages and cities across the US. And again, in a major transit facility like ours, there definitely were some opportunities to incorporate TSP depending on the demand or depending on the urgency of that exact vehicle. So there's some ITS opportunities that we definitely could incorporate into the Vissim model. So Vissim parameters. Just to execute this, again, I touched on this a little bit earlier, but there's many different ways to go about modeling a transit facility. At the previous user group meeting, there were some presentations that had transit-oriented projects, and some of them use transit lines and stops, and that may be advantageous for maybe projects that are in suburban or less urban areas. But given that our project it is in a city that is one of the most congested globally, there was a lot of bus bunching that happens. The intervals or the headways between buses were very difficult to maintain, and we understand that transit lines and stops also have that built-in function to add a variety of delays, and there's mechanisms to add some fluidity to the headway, but we came to believe that vehicle inputs and vehicles and network had a better advantage because there were times where we had to manipulate the dwell time. They were dynamically assigned to different parking stalls, and it was difficult for us to change the stops and the location. Like the assignment of that bus to a gate would change depending on the timestamp of the model. And Amin will go over that, but because of these the advantages of the vehicle inputs and vehicle networks having, as you can see in the screenshot here, public transport has a limited number of attributes that could be modified. Although this may have changed in the 2024 and 2025 Vissim models, but we were living in the 2023 Vissim land. So at the time, we definitely found a bigger advantage of using vehicles and network, which had a much longer list of attributes to be able to dynamically assign vehicles. So that was the justification as to why although this is a transit project, we deviated from transit lines and we utilized vehicle inputs. Scheduling, so what you're seeing here on the right is just a sample schedule of one of the floors. This was the 6th floor of our transit facility. As aforementioned, the peak direction is the departure, so you're going to see a lot more departures buses, and then the arrivals, we landed around 43 arrivals buses and then 149 departures buses. And as mentioned before, 616 and 617, these two gates were the arrivals gates. So the agency informed us that they wanted this because they wanted to reduce the conflict. If arrivals buses were to go to their respective gates, there would be conflict of vehicles not being able to perhaps leave on time or pick up passengers. The queues would perhaps elongate within the facility. So they designated 43 vehicles to 616 and 617. That posed a challenge. Again, as mentioned before, the target turn per gate was 6 to 7. So if you're squeezing 43 into these gates, then that far exceeds what the agency really wanted. However, given that the arrivals passengers are dropping off passengers from the fleet has a much shorter dwell time compared to departures, buses that are leaving with passengers, they still wanted to keep it at 616 and 617. However, for modeling purposes, what we noticed is that when we had just 2 gates, there was massive queuing. Vehicles were not able to be processed. So we ended up opening, I believe, 613 to 628, the ones, the 4 gates prior, and then we ended up having to open up additional gates after 616 and 617. So vehicles are traveling in a clockwise direction that may have not been mentioned prior, but essentially vehicles would come, and if they recognize that there's no space here, it would be unrealistic for vehicles to continue to recirculate, while the agencies would prefer the arrivals vehicles to lay down here. They may be forced to lay down in this area. So that was one assumption that we built into the model, and some adjustments had to be made due to the capacity and the demand of this particular floor. What you're seeing here from 6:18 to 6:30, we had some articulated buses. So Amin will share some video footage of what an articulated bus looks like. And one of the challenges or opportunities is a better word, is that this transit facility does not only deal with one or two bus agencies, but multiple. So we had different types of fleet, different shapes of fleet, different destinations, obviously. So there had to be a designated area for the articulated local buses in comparison to the express buses that were assigned from 601 to 628. So the articulated buses were at the end of the stall, and the length of the sawtooth parking stalls were maybe about 20 to 25% longer than the regular stalls. Gate assignment. So the logic behind it essentially was arrivals buses would be directed to gate 16 and 17, as discussed, 616 and 617. If they're occupied, they would use the parking stalls upstream. Articulated buses would use the gates after the arrivals gates. And then again, if there was an arrivals articulated bus, and if they were unable to find any stalls at 616 and 617 in the upper right-hand corner, then they would be free to utilize any of the stalls preceding that. So that added a little bit of more noise for the departures buses, if you will, but it definitely reduced some unnatural continuous recirculation where vehicles were making continuous laps trying to find buses. So this was a strategic move for us, and it was kind of a reality check for what the agency had initially proposed as maybe something that they need to reconsider. Speaking of recirculation, we had one location where we did some major recirculation checks, whether they needed it. And that really impacted not only the capacity is set, but the demand would be impacted by the need for recirculation. So this was a major point of exploration for us. If there was a bus that, obviously wanted to seek a parking stall and be able to drop off passengers, and they were unable to, they would recirculate. If they were able to find an arrivals gate and drop off passengers, but they had an immediate departures assignment where they had to go back to their departures gate, then they would recirculate. If they were assigned to a departures gate and they found it, but that gate was occupied maybe because the bus in front of them, they're delayed, then they would recirculate. And then we had a final recirculation logic, which looked for anything that had a park state of 7, meaning they still needed to park, they would be recirculated. And these layers of adding recirculation checks did drive up the volumes on the foreplate, but that definitely was a lot more of a conservative estimate of the noise and the friction, the congestion that the floor plates would be met. So we definitely wanted to do a more conservative estimate, and these made that happen. The staging area, so this was really interesting, was Levi, who is no longer with PTV. He helped us quite a bit with the logic of this, so credits to him, really appreciated his help here. What you're seeing is the staging area. What's highlighted here are the sawtooth locations, which are the long-term storage for a fleet that stay and have maybe, you know, several hours of headway, or maybe they had an AM peak assignment and they had to hang out somewhere until the PM peak. They would be stored along these sawtooth. And then what you're seeing here in the racetracks here are the racetrack or short-term parallel parking stalls. So what you'll notice is that vehicles will stack up and they will find, you know, they won't hang out in a random spot. They would go to the farthest location where there's a space. And anytime the vehicle would vacate, the track leader here would vacate, vehicles behind it would, you know, at an interval, try to identify whether that, you know, space was occupied or empty. And if it's empty, they would move up so that it would allow for space in the back to continue to grow. And then we had, Amin will go over this, but we had some logic where the track leaders, so up here, these would at an interval check the occupancy or the availability of space at the gate. And so if the gate had a zero occupancy, or there was a capacity to take on a vehicle, then the bus would be released, the dwell time would be cut to zero, and the vehicles would be released, and it would be met with a signal here and be able to continue on to the gate assignment. One assumption that our agency really stressed with us was no PM bus will leave empty. So if there was an arrivals bus that had passengers and that were dropping off in the PM, they would never leave empty. They would always leave from the gates. And given that we had 43 arrivals buses and then more than 100 departures buses, the assumption was that the 100 buses most likely will have been stored during the midday. So maybe they had an AM assignment, but they didn't have a departure. So we would have between 80 to 100 vehicles that were just hanging out here. So while it's ideal to have vehicles move around and stack up in the order of priority, that is difficult to achieve, and that doesn't always happen. So the opportunity to have the frontmost fleet or dynamically assign the driver to the vehicle so that the driver that needs to get to the gate earlier can just pick up the vehicle in the front for the track leader and get released to the gates. So this definitely incorporated and mimicked the outside noise and congestion that's experienced in the local streets. The headway would have, if vehicles were released as transit lines and stops, the amount of noise and congestion and friction that is experienced outside of this facility probably would have been difficult to mimic. But so we were really happy with selecting vehicle inputs. And so that concludes my part, and Amin here will take away. He will discuss the user-defined attributes and then the attribute modifications that were used and executed for all the concepts that we wanted to test out.
All right, thank you, Sherry. So I will present the rest of the slides. And so Sherry talked about what we wanted to do, and I'm going to talk about how we did it. So as we know, every object on Vissim has some attributes. For example, for a link, we have attributes like length of the link, number of the lanes that it has, link behavior, and so on and so forth. So we can modify those behaviors and we can modify those attributes through the simulation for the dynamic simulations. And in our case, in order to modify some attributes, we first needed to define some new attributes for objects like the links and vehicle that we have in a network. Sherry, can you go to next slide? So here, I'm talking about some user-defined attributes that we have, and mainly these are the attributes that we use for staging. So Sherry mentioned that basically there is a way to create the parking lot in Vissim, which is just create just one parking lot and then divide it into different parking stalls. And then we can use attraction parameter for each stall. So in this scenario, we define the attraction for the first stall and the last stall, and Vissim itself randomly assigns buses to those tracks. But that randomness can result some stalls being vacant, and we needed to move the buses to make space for the incoming buses. So to do that, we had to basically the goal that we had for the staging area is to move the buses forward to go all the way to the track leader. And for that, we need first to identify or distinguish the buses that are in the staging area. To do that, we define some attributes like is SA and is in SA. So is SA is attributes for the link. Basically, it distinguishes the links that are in the SA area, which means the parking lots. And then we can look at that for the vehicles in the network or buses in our network and say, is in SA, that's basically, this is a formula base, as you can see on the bottom part. So it is number 21 in the user defined attributes, that there's a if formula for that, which says if we check the link for that vehicle in the network at the time that we check it, and if it is in the SA, we put 1, or if it is not 0. So that's basically 1 or 0 logic. And then if you look at the picture on the right for the parking lot, each parking lot, basically there's a forward lot. So for example, for number 643, the next parking lot is 670, and then 671, 672, all the way to the first one, which is 677. So we defined an attribute that says, okay, what is the forward parking lot number for each parking lot? And then we have the track leader, which is 661, 669, and 677. So basically, again, that's going to be 1 and 0. So, and the track leader, if the link is track leader, we put 1, and if it is not 0, and then we check it for the vehicle also. So if the vehicle is in the track leader or not, again, if logic 1 and 0. And what do we want to change in this user-defined attributes? Lastly, we want to basically change the dwell time. So let's go to the next slide. So here on the right window, I'm showing how buses move forward in the staging area and how we modify the dwell time for the buses. So in the right picture, we have the attribute modification window. And as you can see, the target attribute that we want to change is dwell time, as I mentioned. And at the bottom of that window, you can see the new attribute value that we want to put is 0.01. So basically really a small number. And it checks it every 5 seconds, or if you can see on the period, so it is 50. And it happens for the whole simulation period. So basically it is from time 0 all the way to the end of the simulation. And that objective filter is actually shows how we filter the vehicles that are in the staging area, and also it is available. So basically, if I want to explain that object filter, it first look at the forward lot. So basically the first one is it wants to make sure there is a forward lot for that parking lot, or it is not the track leader. And then we need to look up. We need to look up the parking lot availability for the next parking lot, so or forward lot. So I want to, can you Sherry play the video? So let's check the buses that just get into the network. So it starts to check the availability of the next parking lot. If it is available, it starts to move forward, and it goes to all the way to the basically to the location that there is not any available parking lot in front of it. And it is a dynamic situation that it happens for the whole network every time. So basically, whenever every 5 seconds, we check that logic for each parking lot in the staging area. And then if it is available, the bus starts to move to the next parking lot. And as I mentioned early, so this is just an example of one floor. The actual model has multi-level floor, so it happens for every staging area. Every 5 seconds, it's going to check this criteria. So let's move on to the next one. So now this staging area, so basically we wanted to move the buses forward, and also Sherry, can you go to the next? Okay, so and when it comes to the after the seeding period, which we start to fill out the staging area, now we go to the peak period that we want to study, and then we start to release the buses. Again, in the right picture, we see the attribute modification window. And again, the same thing applies. So we need to filter the buses that are going to be released. And in this example, I just put an example for gates 5 and 6. So basically the same attribute modification applies to all the gates. So it is just one example for one gate, but we do it for all the gates and all the floors. So what happens here, again, we want to change the dwell time and release the car. So the release, if you see the new attribute value is now, it is 0. So basically we want to release it. And the difference between this one and the other one is basically it has a specific time. So if you look at the time that we check it, it is from 1680 to 69. So it is basically the peak period that we are doing the analysis, and it checks it every 180 seconds or every 3 minutes. Again, we need to filter the bus that it is in the track lead and release that one. For this case, I put an example for gate 5 and 6. So basically, first, it needs to make sure that the car that it is in the track lead is for gates 5 and 6. It is vehicle number 205. So basically, for each case, again, we had to define different vehicle type. So this is vehicle type 205, which means it is for gates 5 and 6. And then make sure it is in the SA area. And then it starts to look up the parking lots, the stalls for gate 5 and gate 6. And it checks that those gates are available or not. So that's another way to check the availability. Basically, because it is 2 gates, we need to check it. Basically, it should be less than 2, which means one of those is at least available. And again, we need to make sure that it is a track leader. So when it checks this criteria and it filters that, it starts to release the vehicle. So Sherry, can you play the? So if you look at the first vehicle in the tracks, those should start releasing. So if you see, for example, one at the bottom, it starts to release and it goes to its own gate. And through the way that it goes, it starts to read some partial routes and also some parking lot routes to go to its defined routes. The other one is right now released. So it checks it. The other one also. So basically, it checks it every 3 minutes. And I forgot to mention something. So basically, we color coded the vehicles. So we have some brown ones, which those are only departures vehicle, which goes to the gate and pick up the passenger and leave. The yellow ones are the arrival. So basically, they have passengers. They come to the network with passengers. They go to the gates and drop off the passenger. Then they recirculate and go back and pick up the vehicle, pick up the passengers. Because of that, we have 2 color for buses, and then also we have two type of buses as we talked. So we have articulated buses, which are longer, and then we have also the regular buses. So these are all types of the buses fleet that we have. And let's go to the next slide that we talk about the challenges that we had through this modeling. So the first challenge is the parking attraction, which I mentioned is working randomly, as I mentioned. So basically we need to fill up the whole staging area, and we make sure that there's no vacancy because of all the vehicle queue management system that we wanted. And as we said, so we had to create some dynamic flow for that staging area, which wasn't available with the default Vissim. And then the other problem that we had was about coding the headway and releasing that couldn't match the gate occupancy. So here again, I shared one screen. So here we wanted, at some stage, we wanted to develop the plan that matches exactly the headway. So in this case, for example, for gate number 5 and 6, we know what would be the frequency of the buses for that station. And if you see it on the, over there, basically we changed the dwell time. And in this case, we wanted to make sure that the bus would arrive at the specific time. For example, if we wanted the bus to be at the gate at 5:05, basically we defined a from time to time, and then we wanted to, if the bus arrived at that period of time, so by it's a little bit, so basically we give it a little bit of standard deviations, and we say if the bus arrived at this time, then the dwell time for that bus would be 180 seconds or 3 minutes, which is the time that the agency gave us for the pick up the passengers. But if it arrives in other time rather than that period from time to time, the headway wouldn't change. So basically it just stays at the gate till the next time, till it goes to 5:10, and then it releases at 5:10. So basically it was one try to capture the exact headway. And the problem with that was if you look at this attribute modification, you see we have about 342 modifications for the whole model. And a lot of those needs to check every 5 seconds or every 3 minutes, the whole network. And all of those checkpoints and attribute modifications, all those if, basically the model couldn't, our computers couldn't keep up, and it was computationally demanding, and our model kept crashing. As a result, we had to remove those headways. And Sherry, can you show the final model? So this is the final model and the way that it works. And you see that the staging and moving forward vehicles happens all the time through the analysis. And also we have a lot of buses that go, as we mentioned earlier, we wanted to have some sort of conservative scenario because the current status of this terminal, it's really bad, and then they wanted to make sure that this new facility can handle that volume. And also, as you can see, the terminal, some locations there are 2 lanes, and at some locations there are 1 lane. So they wanted to make sure there's no bottleneck in that design. Well, actually, this one is not the design that the final design of the actual terminal, but so basically, one of the criteria was to make sure there's no bottleneck in the network through all these scenarios that recirculations happens. And let's go to the next slide about the conclusions that we had from this project. So the first thing was about user-defined attributes and attribute modification, which is help us to create some dynamic component to our model. As we know, there are other ways to do that. For example, we can go through that with coding, but in this specific project, the timeline that we had didn't allow us to go through coding. So we wanted to we had to come up with the fastest solutions, and then we find that solution is basically user-defined attributes and attribute modifications. The other problem was with the memory, that it couldn't keep up with all the modifications that we put through that. And the other thing was the case that we use basically the inputs instead of using transit lines and transit stops, because we need more flexibility on our model. And the time that we developed this model, there was no partial parking route, which has, I think it is one of the new features in the new Vissim model. I think it could have helped us if it was available the time that we developed this model, because we had to go through partial route and parking lot. So basically combine those two together to get the flexibility that we want. So now we have formula-based parking routes, probably that can save us some time and basically the computation that we are doing here. And as you can see in our models, we use a lot of dummy connectors and dummy links in our model for static routes, for partial routes, for parking routes even. Those are some checkpoints that helps us to basically visually check the model and make sure it is doing what we want it. So mostly it is for visual inspection, but it helped us a lot. And I think Sherry, you can talk about the other findings that we had here.
Sure. Yeah, just this is the same slide. It recaps kind of what we had explored. So there are some future opportunities for demand management, not just at a transit facility in a very urban area, but even suburban across the country. If there's tight space, or if there's fleet management needs, queuing of fleet that perhaps don't get individual stalls in a tight space, there's opportunities to save on real estate here, engaging in sensors and RFID, and then dynamic gate assignment, being able to adjust the fleet to the driver, to the gate on demand. Amin went over this briefly earlier, but we were looking at gates 5 and 6, and some of you may wonder, why are you doing gates 5 and 6 and not just gate 5 or other combination? Well, the agencies typically will assign, if there's many buses of like 123s, then and it exceeds the 6 to 7 turns per gate, they're going to assign one route to multiple gates. So what you saw at gate 5 and 6 were that there's probably 12 to 14 buses that want to leave on that same line. So they will share the same transit route. So if you have the opportunity to dynamically adjust the fleet to the driver, there's some opportunities there to save on space, or reduce the number of recirculation, or having to back a fleet in and out from these tight spaces of parking stalls. And then driver and fleet coordination from central dispatch, touched on this already. And then bus priority sensors. I think Amin showed the video footage. There's maybe about 2 to 3 pinch points where there's conflicting. These buses are very long, and some of them are multiple axles. So you could see that, in very tight spaces in an urban environment, and you have multiple buses kind of competing for their space in a very tight infrastructure. Being able to understand what bus is priority, or am I lesser in the hierarchy or higher in the hierarchy, will allow for better communication and maybe perhaps less friction and issues within the floor plate itself. So there's some opportunities for TSP as well. So we thought we had a lot of really interesting discussions during this project, and Amin was he helped build the entire model, which I spoke of the 6th floor, but there's multiple floors. He also helped with modeling the ramps, and we hope that one day, you know, once this is perhaps explored further, or you know, we get the permission to share the full model with PTV, we really hope that that day comes, because it really looks cool in the 3D scheme with multiple floors of floor plates of gates, lots of different types of vehicles. The ramp is, you know, very intricate. It deals with a lot of congestion on the local streets. So we look forward to perhaps one day sharing the entire model. So thank you so much. Again, these are our contact information. If you had any questions, or if you wanted to, you know, brainstorm of, perhaps we also want to hear about other transit infrastructure from across the country, we would love to do that. So please reach out. And yeah, thank you so much for listening to our presentation. Thanks, Amin, also.
Thank you, Sherry. Hey, why don't you leave your